Thank you very much for the introduction and for organizing this wonderful workshop. So this is joint work with Har-Peled. So I will talk about locality-sensitive orderings, and I want to kind of introduce it in a general, kind of broad introduction for this. And one can think about clustering. And I see clustering is some random partitions such that nearby points are likely to get together. And they're very useful for different divide and conquer approaches. And taking this clustering approach one step forward, we have this notion of cover, which is just a collection of clusterings or partitions such that we get some success on any pair of points that's in one of these partitions. That is, like every ball is inside cluster in one of these partitions. And in this context, locality-sensitive orderings, it's something that taking this even one step forward and giving some additional structure on such covers or clustering. So let me start with the definition of tau rho locality-sensitive ordering. So given symmetric space X, this locality-sensitive ordering, or LSO, is simply a collection, sigma, of orderings. And ordering is just like permutations or some orders on these metric points. And this number of orderings is bounded by tau. And for every pair of points X and Y, there are positions somewhere in each order. And the guarantee is that there will be some special order sigma, such that without generality, X comes before Y sigma. And all the points between X and Y in this order could be partitioned into a prefix and a suffix, such that all the points in the prefix are very close to X, that is, are placed in the ball of radius rho times the distance between X and Y. And the suffix are placed in the same way near Y. So in a sense, you are guaranteed that you have a bunch of orderings, and they guarantee that in one of them, every pair of points will kind of be nearby, in the sense that they might be like far away, like in the order itself, but all the points between them are like very close to one of them. So in a sense, this is the way of these LSOs, a way of reducing different problems to the line. And we'll see some examples soon. So what is known? So Chan, Har-Peled, and Jones introduced this notion of LSOs, and they showed that for every set of points in d-dimensional Euclidean space, one can construct an epsilon to the minus d epsilon LSO. That is, the number of orderings will be exponential in the dimension, and this epsilon could be arbitrarily small. So they constructed these orderings using this notion of space-filling curves. So in a sense, consider you have some box, let's say in 2 dimension, and you have these Z shapes. And this means that I want to place all the points in the space into one order. So I decided all the points in this lower left rectangle will become first, and then like this rectangle, then this one, and this one. This kind of define some part order on kind of these big groups, and then you recurse in each group. So here you have this, again, this Z shape on the lower rectangle, and in each one of them, and then you continue this recursively, and you get kind of an order on the entire space. Yeah, so this is kind of space-filling curves, and now to get kind of satisfy all pair of points, you can make another order, like this kind of translated Z, and now you can see that every pair of rectangles are consecutive in one of the orders. Yeah, so for every pair of points, there will be some kind of order when the rectangles will come one after another. And this will be enough already to give you some LSO with like constant epsilon. And if you want to get this epsilon to be arbitrarily small, so instead of partitioning this rectangle to like 4 parts, we'll partition it to like 1 over epsilon in each dimension. So it will be like epsilon to the minus d. And you take some order. And now one can show that if you take epsilon to the minus d orders, you can ensure that every pair of points, like every pair of rectangles, will be consecutive in one of the orders. So we have this order with this first, this second rectangle, so and this third, and so on. And using epsilon to the minus d orderings, it's enough kind of to satisfy all the rectangles, and therefore every pair of points will be consecutive in a sense. In one of them, in all this rectangle area around them, will be in the middle of the LSO. So we'll see some more examples of this soon enough. Okay, so one application, like very simple application of this LSO, just to show you why they're good, is for nearest neighbor search. So suppose that you constructed this LSO for the entire space, and you kind of keep the positions of all the points in your data set, and then you receive a query. So you can put this query in each one of the orderings and check your neighbor to the right and to the left, and just take the nearest neighbor in all the points that you check, and this will be approximate nearest neighbor. Yeah, so suppose that y is the nearest neighbor of x, and this is the ordering that guarantees you that all the points between them are close to either x or y. So all the points here will fall to the ball around y, and therefore z here will be a 1 plus epsilon approximation to the nearest neighbor of x. Yeah. So Chan, Har-Peled, and Jones show some additional applications. So they show how to construct this LSO in dynamic fashion, and they get dynamic nearest neighbor search, closed pair, and some dynamic spanners. And after them, there was some papers by Buchin, Heracle, and Oláh, who showed some application to reliable spanners, which we don't know any other way to construct other than these LSOs, and we'll discuss them in much more detail later in the talk. So the plan of this talk is the following. So we'll start with talking about doubling metrics and how we construct the LSOs there. Then I'll come back to discuss these applications to reliable spanners. And then we'll talk about some different types of LSO that we can construct in other metric spaces. So by the way, feel free to interrupt me at any point. So yeah, so let's discuss doubling metrics. So doubling metrics are in a sense generalization of Euclidean spaces, so the notion of dimension. We say that the metric space has doubling dimension D if every ball of radius R can be covered by at most 2 to the D balls of half the radius. So here you can see that the red ball is covered by 7 balls of half the radius. And this is indeed the generalization. It is known that every D-dimensional Euclidean space has doubling dimension asymptotically D. And there is a class of results showing that the things that you can do in the Euclidean space you actually can do in this much more general notion of doubling dimension. And the most important property of doubling metrics is this packing property, which says that given a set n of points, such that every pair of points are a distance at this delta, and they all live in all of radius r, then the number of points is bounded by this r delta to the power of the dimension. Okay, so Chan, Har-Peled, Jones are actually in their original paper already tried to attack doubling metrics, and they show that every doubling metric with doubling dimension D admits an LSO with number of orderings being epsilon log n to the D. And this is somewhat unsatisfactory because in generally we want the number of orderings will be independent of the number of points. And especially log n to the D is quite significant loss here. And our result here is that actually we can get LSOs for doubling metrics with a number of orderings epsilon to the minus D, which is the same as Euclidean spaces. So let's discuss how we construct these LSOs. There's several tools and notions that come into this theorem. And the first one is a notion of HSTs, or hierarchical well-separated trees. So in a sense, HST is some very restricted type of metrics. We say that a metric space X is an HST if we can map the points of the metric space X into the leaves of some labeled tree. So this is a tree, and there's some function label mapping the points of the metric space into the leaves here. And each internal node has some label. These labels are monotone, that is like Li is more than Ld, which is more than Lb, and so on. And the distance between 2 points is defined to be the LSA, like the significant ancestor of 2 points. So like the distance between V3 and V5 will be the label of this LCA, which is LD. And the distance between, say, V8 and V11 will be this label, which is the maximum distance in the metric. So these metrics are, very easy to construct algorithms for, and they have lots of nice properties. And we need another property of them, which we call K HST. In addition, the requirement is that there's a multiplicative gap between 2 consecutive labels of at least K. Yeah, so you have this label LB should be at least k times larger than LD, which will be by itself k times larger than Li, and so on. So this calls an KHST. And for this talk, what is relevant is that if you have a KHST with maximal degree delta, which is like, so here the maximum degree, I guess, is 4. But if you have a KHST with maximal degree delta, then you can construct for it delta over 2, 1 over k LSO. So number of orderings will be delta over 2, and the gap, the guarantee kind of the radius, will be 1 over k. That is, that for every 2 points, there will be some orderings, when all the points between them will be partitioned into prefix and suffix, such that all the points in the prefix will be a distance at most 1 over k times the distance between the 2 points. And let's see, so the proof is by induction. So consider your HST. And so this is the highest label, like the root of the tree. This is all its children, which number is most delta. And suppose that we already constructed an LSO for each one of the children. So for each one of these kind of children, there is some, it's defined some HST, and we constructed an LSO for it. So there's like a delta over 2 orderings here, such that every pair of points inside is satisfied. And now, to get a global ordering over all the points, we take kind of these internal nodes here, LA to LG, and we order them between them as nodes. And one can show that using delta over 2 orderings, you can ensure that for every 2 nodes here, there will be some ordering when they are consecutive. So, I mean, if you take delta square, for example, it's very easy to see this property, because I mean, there's just delta square edges in the clique. But actually, delta over 2 orderings are enough. This in a sense because you can cover all the edges of a clique using delta over 2 Hamiltonian paths. Anyhow, and now take these orders and simply plug in here the previous orders that we're constructing inductively. So here we have all the first order for each one of the children. We simply replace him in the first order constructed for the global, and the same one for each one of them until the last order. And this is actually already an LSO. So let's see it. Consider a pair of points, which need to show that there are some orders that satisfy them. So if the children of like the same internal label here, internal node here, so by induction, one of these orders will satisfy them. So we are happy. And from the other hand, if they're coming from different children here, suppose X comes from LB and Y comes from LF. So by the guarantee, there will be some order where we construct such that LB and LF are neighbors, like consecutive. And therefore, in the ordering that we construct in the end, all the points here comes from some order of LB, but all the children of this internal node LB, and all the points here are children of this internal node LF. And therefore, every point here in the middle, this comes either from LB or LF. And suppose like this point Z comes from LB, and therefore distance between X and Z will be the label of this node. And because this is a KHST, this will be K times smaller than the label of the root. And the label of the root is simply the distance between X and Y. So we get our guarantee. Okay, so the bottom line is that these KHSTs admit very good LSOs, at least when they have a small maximum degree. And now the idea to construct LSOs for doubling metrics is to, in a sense, construct a cover of all the points in the doubling metric. So we try to construct a bunch of HSTs, such that each pair of points in doubling metrics will be kind of truly represented in one of these HSTs. And then we construct LSOs for each HST. It will be an LSO for the entire doubling metric. So more formally, we have this definition HST cover. It has 4 parameters, tau, rho, k, and delta. And an HST cover of a metric space X is a collection of tau k HSTs. So we have tau like HSTs here, and each one of them is a KHST. And the maximum degree of all of them is delta. And the guarantee, and the interesting guarantee here, is that for every pair of points X and Y, there will be some HST in this collection, such as distance in this HST will be at most rho times larger than the original distance, while like all the distance will be dominating. So you never shrink any distance in any one of these HSTs. And the theorem is that every space with W dimension D admits a good like, HST cover when the number of trees is epsilon minus D, and this row is very small, it's not as epsilon, so it's very truly represented the actual distance. The maximal degree is 1 over epsilon. No, sorry. The K here, kind of the gap between two consecutive levels, is 1 over epsilon, and the maximal degree is also epsilon to the minus D. And now, because we know that every KHST has maximal degree delta, with maximal degree delta, it means a good LSO. So we can take this HST cover, we construct an LSO for each one of the HSTs, and this collection will be an LSO for the entire metric space. So this is how we get our theorem, that every metric space with W dimension D admits this type of LSO. So let me tell you something about how you construct this W dimension, this HST cover. So for this, by the way, do you have any questions? I guess I'm going very fast and nobody asked anything.
Hey, Arnold, can you hear me?
Yeah, hi, Eric.
Maybe it's a naive question, but so why doesn't the reduction lose a factor of 2 over delta at every level?
You mean here?
Yeah.
In this? So right. The idea is that you construct order over the nodes here, but you plug in this order, so you don't lose anything like in the number of orderings, because like you have a certain number of orderings here, which is the same as the number of orderings you need like for these global nodes, and then you just plug in them inside. So you don't need to plug each one everywhere. It's enough to plug it only once.
Okay, I see.
More questions? Okay, so yeah, we've been here. I wanted to discuss how we construct this mysterious notion of HST cover. And for this, we used what we call a pairized partition cover. So generally, in many type of these partitions covers, the guarantee you usually get, like in LSH, for example, is that given some point, there will be some cluster such that some ball around this point is kind of likely to get inside one cluster or something like this. And this is like very useful, but it's not strong enough for our case, because we want to get this 1 plus epsilon. And forget 1 plus epsilon is not enough kind of to be in the middle of a cluster, because then you already lose a 2-factor. In a sense, what we will get here is that given 2 points, that would like in some cluster exactly kind of the edges of the cluster, and like you will not lose only 1 plus epsilon factor. So let me try to be more formal. So we're discussing here. So the notion is tau, rho, epsilon, delta, again, 4 parameters, pairized partition cover. So this is a collection of partitions. So this is like one partition of the space, second tau partition. And the guarantee is, so the first guarantee is that every partition is delta bounded. It is in every cluster, in every partition, the maximum distance between points is at most delta. This is just the distance parameter. And the second guarantee is that for every pair of points x and y, the distance at most delta over rho, so rho is some parameter, which will like be quite small, like 1 plus epsilon. There is some cluster in one of the partitions, such that both x and y belong to this cluster together with some small balls around. So we get some clusters such that the ball of radius epsilon delta around x and the ball of radius epsilon delta around y are together in this cluster. In a sense, this is the best you can hope for, because the diameter of the cluster is almost equal to the distance with x and y. So you can construct such pairized partition covers with W matrix when the number of partitions will be epsilon to the minus d. This rho will be 1 plus epsilon. and delta is just a parameter. You can choose it whatever you want. So let me tell you how we construct this pairwise partition cover. So the idea is that you take some net, which is the red points here, and by net I mean that it's a bunch of points such that every point in the metric space is a distance at most epsilon delta from some net point, and the pairwise distance between every two net points is at least epsilon delta, right? So like you can cover the entire space by such small balls, and the distance between every two is large. And now, given this net, we take some matching. You can think of maximal matching between net points, a distance most delta over rho. Yeah, so this is like a matching. It's just matching. And given such a matching, we construct a clustering by taking every edge in the matching and taking the two balls radius epsilon delta around the net points. So here we have the orange cluster and the gray cluster and so on. And the rest of the points we just partition on the chart. Don't care about them. So intuitively, why this would be good? So we can think of 2 points, and you need to satisfy them in one of these partitions. So they will be close by to some net points, and these net points, if you match between them, then these two clusters will be exactly great for them, because the diameter of this cluster, like the orange cluster, is almost equal to the pairwise distances of every pair of points in like left and right parts. So now we repeat these matchings until every pair of net points distance at most delta over rho is matched. So we take some matching, and then kind of all these pairs satisfied, we take another matching, and so on. And by packing property, you will be done after epsilon to the minus d matchings. Because kind of if a pair doesn't get matched, there's a reason for it, and this reason could appear only bounded number of times. This is clear? Yeah, okay. Yes, so now I'd like to show that pairwise partition cover implies HST cover. And the idea is that you take a pairwise partition cover for like a bunch of different scales. So we take some alpha here, which we'll use for the entire construction. It's just some number between 1 and 1 over epsilon. And then we construct a pairwise partition cover when the delta is alpha times epsilon to minus I, this minus is growing. So in this, like in the beginning, alpha is very small, and then each step we're taking larger and larger like diameters for the clusters. And the gap between two like levels is quite large. It's 1 over epsilon. Yeah, so we constructed the pairwise partition cover for all the scales, and then take the J kind of partition from each one of the covers. And our hope is kind of to make an HST out of this partition, because HST is just like a hierarchical partition, laminar partition. The problem, however, this partition was constructed independently, and there is no reason that they will be laminar. But because the gap between every two levels is so huge, like 1 over epsilon, we actually can force them to be laminar. So I mean, for example, think that this colored partition is the highest level, and the black partition is the lower level, and you want them to be laminar, so you just force them. Since you take all the clusters that cut anything in the green here, and you make it to be the first cluster, and so on. And because kind of each cluster, the lower partition is like only epsilon delta, so it's fine. You don't do lots of damage. And now, once you force it to be a laminar partition, this is just induces HST. Yeah, because the internal nodes is just the name of the clusters in laminar partition, and then the label of each node with the diameter of the cluster. And this is already will be the HST cover that we hope for. So we did consider a pair of points X and Y, and suppose that this is between them is delta. So by pairwise partition cover, there will be some cluster such that these two balls around X and Y of radius epsilon delta are inside the cluster. And the cluster is only has diameters slightly larger than the diameter, than the distance between x and y. And now in the HST that we constructed to be associated with this partition, their distance between x and y will be the diameter of this cluster C. In a sense, we force it to be something different, maybe C tilde, but I mean, because of these both are large enough, so they're still in the cluster, and the diameter of the cluster is about the same, and therefore we get our distance guarantee. Finally, the maximum degree of this HST is bounded again by some packing arguments. Just because you construct a net and the number of net points inside like a both larger net is bounded. So just to wrap up this, we show that every metric space with dimension D admits this good HST cover, and this implies a good LSO. So this is all what I want to say about doubling metrics. So it's a good time to ask questions about this part of the talk. Okay, so if there are no questions, we'll move to the second part, which is about reliable spanners. So I will start with the definition of metric D-spanner. Given symmetric space X, a metric spanner is some graph H over the metric points, so like this, such that the weight of each edge is simply the metric distance between the 2 points. And we say that the spanner has stretch T if for every pair of points X and Y, the distance between them, the shortest path distance in this graph is at most T times larger than the metric distance. So for example, this X and Y has this path of 3 edges between them, and the sum of the weights should be at most T times larger than the original metric distance. So generally, like spanners, the goal is to construct sparse spanners such that this T parameter is small. This is a very well-studied notion. And reliable spanner is a kind of generalization. It's a very resilient structure. The idea is that this is a spanner that should withstand like a massive falls of nodes and still be able to connect whatever remained. So formally, an H is a new reliable T-spanner of the metric space X if for every attack B, so like think of the scenario when you have some attack B, for example, some pandemic or something, and lots of places get closed down, and so you have some attack B, and the guarantee is that there is some superset B plus, like there's some additional sites that may be out of service, or you have like bad guarantees for them, and this superset should be only slightly larger than the attack B, so only like by mu fraction. And for every pair of points X and Y which are not in this superset B plus, the distance between them in the spanner, when you removed all the attack nodes, you can use the B plus nodes, like which are not in B, will be at most T times larger than the original distance. So this is very, very strong. I mean, you can see that if this mu, even say 1 over 100, and your attack is 90% of the network, then the remaining 10%, 9% of them will be like very good connected, even after this huge attack. So Buchin, Har-Peled, and Oláh showed the meta theorem that given an LSO, you can construct reliable spanners. And specifically, like if you have the tau epsilon LSO, then for every U, which we call the reliability parameter, and this governs the size of the superset B plus, every metric space with this type of LSO admits a 1 plus the order epsilon spanner, your reliable spanner, and when the number of edges is n times some polynomial in tau, which is number of orderings, divided by the reliability parameter. So taking the Chan LSO for Euclidean space, just plugging it here, and you get that every set of points in Euclidean space admits a new reliable 1 plus epsilon spanner with number of edges being n times epsilon to the minus d times the polynomial reliability parameter. So this is very good just to get some sense. If you don't require any reliability parameter, just construct a spanner for Euclidean space, so the best you can do is n to the epsilon to the minus d. So what we lose here is this some constant in power of epsilon. And now if you just plug in our doubling dimension LSOs, you get the same type of result as for Euclidean spaces. And I mean, there are some other ways to construct reliable spanners, but they're much worse like this. The function of b here will not be 1 plus nu, just something b squared like this. So in a sense, this is the only way to actually know how to construct this type of structures. Yeah, and the idea of these constructions and this meta theorem is that you can construct a very reliable spanner for the path graph for the line, and then you construct such a spanner for each path in the LSO, and you take the union of them, and this will be an LSO. This will be a reliable spanner for the entire graph. Yeah, so so this works wonderfully for Euclidean spaces and for doubling. However, what about other metric spaces? I mean, we still want to construct some reliable spanners. What can we do? And unfortunately, not much. So Har-Peled, Mendel, and Oláh show that for like every reliability parameter mu, every mu reliable t-spanner for the uniform metric has this polynomial number of edges. So like just take the uniform metric is when all the distances are 1. So even for this very basic metric space, you cannot get linear size spanners if you want reliability for any like constant t stretch. And uniform metrics actually also catches trees and HSTs, like because if you look on this star, so the metric induced on the leaves is uniform metric. So even for like very simple metrics like trees, you cannot get anything good if you want reliability. And to overcome this problem, Buchin et al. Introduced this kind of relaxation of oblivious reliable spanner. So the idea here is that, I mean, you cannot do anything good, and instead of giving this very strong guarantee that for every attack B, you have a small set B plus, the guarantee is that you have some distribution over spanners, and given attack B, in expectation, B plus will be small, but it might be quite large in some cases. So formally, an oblivious mu reliable t-spanner is a distribution over spanners such that for every attack B, there is a superset B plus H. So this is a superset that depends both on the attack B and on the spanner that you sampled H. And so again, there's distribution of spanners, and for every attack B, you have some B plus H, which is superset. And this superset in expectation is only 1 plus mu times larger than B. So I mean, in most cases, kind of you expect it to be small, but it might be some very unlikely case that it would be huge within like the entire space, maybe. And the other guarantee is that you'll expect that for every spanner with the support, and for every xy which are not in the superset, with respect to this spanner, the distance between any 2 points in the remaining spanner will be at most 8 times larger than the original metric distance. And now, given this relaxation, it's already possible to construct some spanners. So specifically, Har-Peled, Mendel, and Oláh show that for every endpoint tree metric, you can construct an oblivious mu reliable tree plus epsilon spanner with number of edges being n times log square phi divided by mu epsilon. So this phi is an aspect ratio, which is the ratio between the maximum and minimum distance in the metric space. And I mean, a priori, it could be unbounded. So this is a term that we usually like to avoid. But I mean, in most cases, it's polynomial, so it's fine. So what is this tree plus epsilon? Is it good? Is it bad? So one observation is that if you take this uniform metric or the tree, then for every stretch parameter smaller than 2, you must have n square edges. Right? I mean, this is true even if you don't want reliability, any spanner, because if every 2 points here, if you don't have an edge between them, you need to go through some other edge, and you already get stretch 2. So you cannot get better than 2, and they get 3 plus epsilon, and there's like open gap here with 3 plus epsilon and 2. And so they constructed their oblivious spanners by sparse covers. In a sense, the idea is that they partition the graph into clusters in many, many different scales, such that every 2 points there will be the same cluster at some point. So, and then they constructed this oblivious reliable spanners for each cluster. When they think about each cluster as a uniform metric or a clique. So in a sense, they reduce the problem from trees here to cliques. And this is the reason they get this aspect ratio. And our idea is to reduce the problem, instead of reducing to cliques, reduce it to the lines. In a sense, use again this notion of locality-sensitive orders. Which like taking space and reducing to the lines. However, it's not really clear how to construct a locality-sensitive ordering for a tree, for a uniform metric. Because I mean, you cannot get these epsilon balls around them, partition prefix and suffix. This simply will not work. So we get a slightly different notion, which we called left-sided LSO. So yeah, a left-sided LSO is a collection again of orderings. But in this case, it will be partial orderings. So this point X will be part of some orderings and not part of some others. And yeah, and the guarantee, like for being tau rho left-sided LSO, that each point X will belong to at most tau orderings. So the overall number of orderings is unbounded. I mean, will be like post-linear. And for every pair of points X and Y, there will be some special ordering, such that both X and Y belong to the ordering. And the guarantee is for every X prime and Y prime that are to the left of X and Y, the distance between them is at most rho times larger than the distance between X and Y. Yeah, so here X prime comes before X, Y prime comes before Y, and the guarantee is that the distance between X prime and Y prime is smaller than the distance between X and Y. This also holds like if Y is way to the left. So just to get some notion of this definition, we can show that every tree metric admits a log n1 left-sided LSO. I mean, that is for every every point will belong to at most log n orderings, and the row here will be 1. So this is actually small. So let's see how this construction works. So consider a general tree and pick the separator of the tree, which is some special vertex, such that every connected component in the tree without this vertex has at most half of the vertices. And we construct an ordering with respect to distances from the separator. So the separator will be first, and the second vertex will be the closest one to the separator, then the second closed, and so on. And the last vertex will be the vertex farther from the separator. And now we delete the separator, and we continue recursively. That is, we take a separator in each one of the connected components, we construct an ordering with respect to distances to these separators, in which one of the connected component independently. So I mean, now there are 4 orderings, and each vertex belongs to 2 orderings. Now again, you delete the separators, you delete all the singletons, and then you continue. And that's it. So one can show that every vertex has most log n orderings, and this is because each time you construct an ordering, the number of vertices in your connected component drops by a factor of 2. So you construct at most log n orderings. And let's see that you have this distance guarantee. So consider X and Y, and and so they were separated at some point, and let V be the separator that separated them. So in this picture, this is X, this is Y, and this vertex separated between them. And we constructed some ordering with distances with respect to this separator. Now, for every pair of points X prime, Y prime, which are to the left of X and Y, we know the distance between X prime to the separator is smaller than the distance between X and the separator, because it's come before. The same goes for Y prime. So now the distance between X prime and Y prime will be smaller. I mean, the distance if you go through the separator And this is smaller as if you go to the separator between x and y, and which is the actual distance between x and y. So we get the guarantee. Okay, so now I would like to show you how to construct reliable spanners using this notion of left-sided LSOs. And as I said before, to construct reliable spanners of the usual definition from usual LSOs, you just construct a reliable spanner for each path. And the idea here is, again, to construct a spanner for each kind of path or order that you constructed. However, I mean, they're quite strange because of this left guarantee. So you cannot simply construct the usual spanner for the path. And what you need to construct is this weird term of left spanner. And left spanner, in a sense, instead of going like given 2 points, you want to go between them, you want to go to the left and come back. So a 2-hop left spanner for the path graph is some graph, such that for every pair of points, VA and VB, there is some point to the left of them, such that both of them are neighbors to this point. So in the usual definition, it's just nonsense, because like taking this all the edges from this leftmost point, giving you this spanner. So this is like easy. However, what we would like is to get something reliable. So a new reliable 2-hop oblivious left spanner. So this is already something more complicated, some distribution over spanners over this path graph here, such that for every attack B, there is some superset B plus, which is smaller expectation. And such that for every pair of points B and DB, there will be some which are not in the superset, there will be some point to the left of them that you such that both of them connected to this point. Yes, I mean, you can like delete all the prefix, and still you will need that most of the points can go to the left and remain connected. And this is possible to obtain. So one can construct this kind of reliable 2-hop left spanner with number of edges will be just the n divided by the reliability parameter q. And yeah, and now kind of you have this meta theorem that says that, uses this left-sided spanner to show that if you have a tau row left-sided LSO, which is this notion we show for trees, you can construct an oblivious, reliable 2-row spanner. So like you have 2-row with number of edges, just n, which is the number of vertices, times the number of ordering square, and divided by the reliability parameter. So yeah. So the idea of the construction is to just you take all the orderings that you have in the collection, and for each one of them, you constructed this oblivious left-sided spanner. So you have this left-sided LSOs, and then for each order in the collection, you construct you sample since because it's distribution over spanners, so you sample and you over tau reliable 2-hop left spanner, and so this is just this type of creature for each one of the orderings with this number of edges, and then kind of the spanner for the entire space will be simply a union of all these left-sided spanners for each one of the orderings. So to bound the number of edges, this follows by the fact that each vertex belongs only to like tau orderings. Like the number of orderings in total is huge, maybe, but each vertex belongs only to a small amount. So overall, the number of edges is bounded. And I mean, if you consider an attack B, so each vertex belongs to tau orderings, it kind of multiplies its attack tau times. So in a sense, this kind of set B plus will be simply take the set B plus in each one of the orderings, and you take a union of all of them. And because we took this slightly smaller reliability parameter, we get that the overall size, this expectation, of course, of this B plus is small. And just to get why the distance is small, so consider a pair X and Y, which are not in set B plus. So this means that there is some, so we know because of the LSO, there's some ordering satisfying them. And in this left-sided spanner of this ordering, they also was not in the set B plus sigma. So this is X and Y, and this means that there was some vertex to the left of them, such that both X and Y have edges to this vertex. And because of this property of the LSO, the distances to the left are smaller, so the distance between X and Y going through Z is at most rho times the distance between X and Y. You have these two edges, so overall it's 2 rho the distance, 2 rho times the distance between X and Y. Oh, yes, this finishes this meta theorem. Yes, so we showed that previously that every tree admits a log n1 left-sided LSO, and now if you plug in into this meta theorem, you get that every tree metric admits an oblivious, reliable two-spanner with number of edges being n times the reliability parameter. And just to compare with the previous result of Har-Peled et al., they get triple epsilon, and this aspect ratio kind of avoided this aspect ratio, and we also get 2. So triple epsilon, and this 2 is actually tight, because getting anything below 2 requires n square edges. So all this story does not end with trees. You can construct left-sided LSOs for tree-width graphs, planar graphs, and free, with stretch parameters being 1 or around epsilon. And this all, of course, implies oblivious reliable spanners in the same like meta theorem, improving previous results. So yeah. So let me wrap up with some open questions. So the first open question is about general metric spaces. So we did not discuss today general metric spaces, but you can construct reliable spanner for general metric spaces. And Har-Peled et al. In fact showed that for every metric space, you can construct a deterministic, pure reliable t-square spanner with number of edges being n to the 1 plus 1 over t. So this is like second order terms. While the only lower bound that we have is that for stretch t, you must have n to the 1 plus 1 over t edges. So, I mean, given n to the 1 plus 1 over t edges, we know how to construct t-square spanner, and the lower bound is only t. So there's a gap between t and t square. And this will be actually like interesting to understand what could be done. Another open question is about planar graphs. Using this kind of techniques of LSOs, you can construct an oblivious neuro-level 2 plus epsilon spanner with linear number of edges. Well, the only lower bound we have is the same like for trees, that getting below 2, you must have n square edges. And so it will be interesting to understand if you can get all the way to 2. Or if you go closer to 2, the number of edges goes up and becomes polynomial. And the final open question is just to find more applications for this new and cool notion of LSOs. That's all. Thank you.